Hello. In this video, we are going to derive the first two of the Maxwell relations, and in our second video, we will derive the other two. The Maxwell relations are named for the Scottish physicist James Clerk Maxwell. Maxwell is perhaps most famous for the Maxwell equations, the laws of electromagnetism. Maxwell can claim to be one of the very few physicists that we will put in the same league as Sir Isaac Newton and Albert Einstein. Suppose that we encounter an expression as follows: m dx plus n dy, where m and n are functions of both x and y. We can say that this particular expression is exact. So here's the word we use, exact. So it's an exact differential. And this is if and only if we take the partial derivative of m with respect to y, and we take this partial derivative, it's going to be equal to partial derivative of n with respect to x. And this is under the condition of constant x, and this is the condition of constant y. If this relationship is true, then this expression is an exact differential. If this isn't equal, then this expression is not an exact differential. Recall that we can write an expression for the exact differential of the internal energy, U. Recall that we could write this as TdS minus PTV, and we were able to do so because this is the combined form of the first and second laws of thermodynamics, or in other words, this is the fundamental equation. We also know, because the internal energy is a state function, that we can write an expression for the differential, again as a function of the variables s and v, and we know that the coefficient for the ds part has to be the partial derivative of u with respect to s. And similarly, the coefficient for the dv, it's doing it from first principles, we know that it has to be the partial derivative of u with respect to v. And this is under condition of constant entropy, and this is under a condition of constant volume. If we were to set the two expressions for du equal to each other, then we know that the coefficients of the variables have to be equal. So that tells us immediately that the partial derivative of u with respect to the entropy at constant volume, this particular expression, the coefficient of ds, has to be equal to this coefficient of ds, which is simply the temperature. Similarly, this particular partial derivative, the change in the internal energy with respect to the volume at constant entropy, has to be equal to the coefficient minus p. So these things we've done before, but now we're going to apply this idea about exact differentials to derive further relationships. We already know, because the internal energy U is a state function, that this particular expression here is an exact differential. We already know that. So as a consequence of already knowing that this expression is an exact differential, then we know that the partial derivative of t with respect to this variable, to the volume, is equal to the partial derivative of the negative pressure, so let's put a minus sign in front, with respect to this variable, which is the entropy. And we notice that in forming this particular derivative, that we kept the entropy constant, and we notice that in this particular case, we kept the volume constant. So as a result, we have derived the first of the Maxwell relations. And note that we were able to derive this starting with an expression for the internal energy U. We will proceed in this and the next video in deriving the remainder of the Maxwell relations using virtually the identical technique. For the first relation, we began with the internal energy U. For the second example in this video, we are going to begin with an expression for the enthalpy H. Recall that we can write an expression for the differential of the internal energy U as TdS minus PdV, which is our fundamental combined equation. Also recall that by definition, the enthalpy H is equal to the internal energy U plus P times the volume V. From that, we can write an expression for the differential of H. It's a differential of U. And then we use the product rule. So we have a product of two functions here. So the differential is going to be the first times the differential of the second, which is dV, plus the second function v times the differential of the first, which is dP. Next, we want to substitute our expression for du into our expression for dH. So we'll show how that goes. And we notice that these two expressions cancel. So our expression for the differential of H here is going to be TdS plus VdP. Now we can use the fact that the enthalpy is a state function, so that allows us to write something which we know is an exact differential in terms of the variables S and P. And we know that the coefficient here has to be the change in H as a function of the entropy S at constant pressure. And the coefficient here has to be the change in the enthalpy H as a function of the pressure at constant enthalpy. Again, effectively, we set the two expressions for dH equal to each other. And as a result, we know that the coefficients of ds and the coefficients of dP have to be equal. The two expressions are always equal. So that tells us that the change in the enthalpy as a function of the entropy at constant pressure, this coefficient has to be equal to that coefficient, which is T. Similarly, we know that this coefficient here, the change in the enthalpy as a function of the pressure at constant entropy, has to be equal to the volume. We're just setting the coefficients of variables equal to each other in equal expressions. That's why these assignments are completely legitimate mathematically. Since this expression is exact, we know that a certain derivative of this variable has to be equal to the derivative of that variable. So we know that the change in t with respect to p, so with respect to, take the derivative of this function with respect to that variable, has to be equal to the derivative of this function according to this variable, which is the entropy. And we know over here it has to be constant entropy, and here is constant pressure. Therefore, as a result, we have derived the second of the Maxwell expressions. And this is the one that we get by starting with an expression for the enthalpy. Thank you very much for your attention. Have a good one, and be ready for the second video where we derive the remaining two Maxwell relations. I thank you very much for your attention. Have a good one.